All right, let's finish up our journey with gases. We'll talk about three things today. We're going to talk about really how gases mix together. And then we're also going to talk about the fact that, you know what, gases really aren't ideal. So in like real life, they don't always follow what we call the ideal gas law. So we have to approach those types of things and just discuss them for a second. All right, so how do gases move? Well, gases mix together. We know this. We probably thought of this in our minds when we were running the gas law experiment. The hydrogen was produced and it mixed with the atmospheric gases inside of the Erlenmeyer flask. We see this every single time that we spray perfume or cologne and it wafts itself through our room. Or we walk up into freshman hall and we smell things that we don't necessarily want to smell. There are gases that are mixing with the atmosphere. And how they do this, the way they do this, is called diffusion. All right, now, another mode that we will talk about and when it comes to the movement of gases is called effusion. Effusion describes the passage of a gas through a tiny orifice into an evacuated chamber. So maybe picture a box, and in the middle of that box there's a partition. And in the middle of that partition there's a small little dot, and you have gases on one side of the partition. And you might ask yourself, how long will it take for some of those gases to move through that little dot in the partition so that they fill the other side of the box? Well, different gases do this at different rates, and that's called effusion. We can actually measure the rate of effusion. The rate of effusion is going to be the speed at which the gas is transferred into the chamber. So we'll get back to that in a second. All right, here we go. Here's effusion. Here's a picture of that. So let's say we've got two different gases. On the left, we've got helium. Okay, and on the right, we've got ethylene oxide. Okay, and I've got the molecular formula for ethylene oxide down there in the bottom. And what you're certainly going to notice right away is that they're probably different sized molecules. And that's good. Good for you. So how should that affect the rate of effusion? Well, logically, right? The smaller little dudes are going to fit through that hole a little bit easier. Thus, they're going to travel into the other side of the box easier. So small little molecules with lower molar masses are going to effuse quicker than molecules with large molar masses. See? That's effusion. Here's diffusion. Look at my little image here. That's pretty sweet. All right, so diffusion is a little bit simpler to think of. There's really no math or rates or anything with diffusion. It's just understanding that, you know, as you uncork the bottle with the perfume, it's going to fill the room up, and those gases are going to mix with one another to obtain essentially the same volume inside of the room. That's diffusion. Okay, plain and simple. Now, as I said before, there's this thing called, we can actually calculate the rate of effusion. And this gentleman named Graham was kind enough to create a law for us. And it's called Graham's Law of Effusion. And it's easy except for one little point. So here's Graham's Law of Effusion. It says that the rate of effusion for gas 1 over the rate of effusion for gas 2 is equal to the square root of the molar mass of gas 2 divided by the square root of the molar mass of gas 1. Whew, that's a lot of stuff. So here's the confusing point, if you're not confused enough already. When you look at the ratio, because by the way, this is a ratio. We never find like the rate of effusion for just one gas. We find, well, how much faster does this gas effuse as compared to this gas? Here's the confusing point. The top part of your little ratio right here, okay, the top part is for gas 1. But in the actual math that you will have to do to calculate the rate of effusion, the molar mass of that gas is down here. Oh, that's crazy. We'll see why in a second. Let me do an example problem in a bit, and I'll show you that. So down here, just M1 and M2 represent the molar masses of these gases. So let's do a nice little example problem that hopefully shows you why it is that these guys are switched, okay? All right, I'm going to take two gases. One really light gas, hydrogen, right? H2, okay? And hydrogen's got a molar mass of about 2.02 grams per mole. Okay? And I'm going to take another gas that's going to be much heavier, UF6. Okay, that's uranium hexafluoride gas, and it's got a huge molar mass. It's 352.02 grams per mole. Okay? Alright, so we want to know the rate of effusion of hydrogen as compared to UF6, uranium hexafluoride. So the problem could be written, something like this. What is the rate of effusion? I'm not going to write it. I'll just take too long. What is the rate of effusion of hydrogen as compared to uranium hexafluoride? Okay, so let's do the math on that. That's going to equal, let's call it the rate of effusion is going to equal the square root of the molar mass of uranium hexafluoride, 352.02, divided by the square root of the molar mass of hydrogen gas. Okay, and if you do that on a calculator and you punch that up, you're going to find out that it's 13.2. Okay, now again, I want to clarify why it is that the numbers are switched around. Okay, so what does this 13.2 mean? Well, it means exactly that. Let me pull up a different color here. It means H2 gas will effuse 13.2 times more quickly than UF6. And so that's why we have to reverse these two, so that we can actually get the right ratio. Okay, if you flipped it, if you did the square root of 2.02 over the square root of 352.02, you're going to get a very small number. And you have to change the verbiage in your sentence. You would have to say, let's say that if you do that, for instance, the number you get is like 0.06. Then you'd have to say uranium hexafluoride will effuse 0.06 times as fast as hydrogen. So you have to change your wording that way. So if you understand the math, you got to understand the wording to report your number correctly. Okay, I also said at the beginning of this video that we're going to take into account the fact that not all gases are ideal. So, when do gases become non-ideal? Well, they're always really non-ideal, but here's where it really becomes apparent. First of all, when the pressure of the gas is really, really high. Second of all, when the temperature is really, really low. What happens with those two things? When the pressure is really, really high, there's like maybe a lot of molecules in the sample. And remember what we said about ideal gases is that we want to say that they don't like run into each other. Well, you put more molecules in, pressure goes up, guess what? The molecules are going to run into each other. So that makes issues. Okay, temperature being too low, then we get some weird stuff to happen there as well. We'll show that in a second. Under these conditions, the concentration of the gas particles is high, and attractive forces become important. When the temperature lowers, it is easier for the molecules to come in close proximity with each other, and so they will attract one another. They huddle with each other like you do when it's cold out. So let's take a look at this really complicated graph here on the right side of the page. Here you've got the ratio of pressure and volume to NR and T. That should equal 1 for an ideal gas, because the ideal gas law is this, nRT. So this side should be the same as this side. So if we go that side divided by that side, we should get 1 for ideal gases. And that's only the case down here. Okay, for very low pressures. See, pressure is 0 here, 0 atmospheres. Once we get higher than 0 atmospheres, we can totally see that ideal gas behavior diverges from the norm. Like, look at, once we get out to 100 atmospheres, which is like a lot of pressure, gases just don't behave ideally, okay, under these pressures, because now we've got different things going on. They're running into each other. They're absorbing each other. All right, so what does this mean for us? Well, it means that our ideal gas law isn't always correct, and so we have to incorporate some changes. Here's the good thing for you. You do not have to do any calculations with real gas laws or the van der Waals equation. I'm just going to show it to you, tell you it exists, show you why the correction factors are in there, and then I'm going to move on. Here it is. Wow, thank goodness we don't have to do anything with that, because that is, well, it's a gorgeous equation, but it's kind of confusing. So here are the correction factors, right? There's one and there's the other. They're both based upon and dependent upon the number of moles in your sample. So, to correct for the pressure and the temperature variances and why gases don't behave ideally, we would have to add the correction factor, or a correction factor I should say, to the pressure side, and we'd have to subtract to the volume side. Okay? So that's interesting. All right, now, like I said, you're not going to have to do any calculations with this, but knowing why we have to add there and we have to subtract there might be important. Okay? Oh, that's corrected pressure, that's corrected volume. Okay, and here's why. For a real gas, the actual observed pressure is lower. Why? Because of the interactions that occur in real gases. Intermolecular interactions. Well, that's weird. Let me give you an example. So oxygen, right? Those are two oxygen atoms, and they're bonded together. And they have lone pair electrons. There we go, there we go, there we go. And you have another one. I don't know if I can clone that. I'm not going to try. So you have another one. All right. Sorry that my oxygen atoms are different sizes. Here we go, here we go, here we go. So they have electrons, lone pair electrons. And each oxygen atom obviously has protons as well. So the lone pair electrons here might be just a little bit attracted to the oxygen atom there. So we get this small little attraction between oxygen atoms back and forth. And this makes things weird. And so we are now non-ideal. See, that's what an intermolecular attraction is that occur in real gases. Blah, 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 blah. Good. Now, the more van der Waals forces, the more, essentially, the larger the molecule, the more opportunities there are for that to happen, thus the less ideal the gas is. So big molecules, not as ideal as little molecules. Okay, also, the total occupied volume difference is due to the space consumed by the atoms and molecules themselves. Remember, one of the other postulates we made when we were talking about the ideal gas law is that the molecules are assumed to take up no volume. I call bubkiss on that because they are molecules. They have matter, they are matter, so they have mass, and thus they have to take up space. It's just a really tiny amount. But when we're talking about real gases, we certainly have to take that really tiny amount into consideration. And again, bigger molecules will take up more volume, so they'll be less ideal. There we go. That's Unit 7 for us, or Chapter 5 of the book. I hope you enjoyed our journey through gases.